Hello dear students, welcome you all. In this lecture, I am going to discuss about an experiment that proves the violation of parity conservation in beta decay, or we can say that disproves parity conservation in beta decay. So this experiment was the most experiment in the history of high energy physics, and this experiment was performed in 1956 by uh, Wu and her co-workers, right? You can see here it was performed in 1956, right, by an Chinese American physicist, Chien-Shiung Wu. You can see here. This is the pic of Chien-Shiung Wu. She was an Chinese American physicist, and she, along with her co-workers, has performed this experiment in 1956 that confirms the violation of parity conservation in beta decay, right? So, coming to the experiment, you can see here, this is the schematic diagram of the apparatus they used for this measurement, and basically they took a cobalt-60 nuclei, right? I'm showing you the reaction that they studied. Yes, you can see here the Bose experiment, cobalt-60 decay. Now, why they took cobalt-60? Because cobalt-60 has a non-zero spin. It has spin 5, and now when the cobalt-60 nuclei are placed in strong magnetic field, they can be polarized. So when they are polarized, then after we will measure the direction of the emission of electrons from these cobalt-60 nuclei when they undergo beta decay. You can see here the reaction that is going to happen. Cobalt-60 is going to convert into, you can see here the reaction, 27 cobalt-60, it will convert into 28 nickel-60 plus electron plus antineutrino associated with electron. Now this nickel-60 nuclei that is formed here, it is in the excited state. It come down to ground state with the emission of a gamma ray, right? So this is the entire reaction that is under observation. Cobalt has spin 5, nickel has spin 4, electron half integral, neutrino, antineutrino half integral. So the spin angular momentum is balanced on both the sides. So this is the reaction that is under observation. Conversion of cobalt into nickel with the emission of electron and anti-neutrino, right? So this is the main crux of this experiment, right? Now you can see here how this experiment was performed. So you can see here the schematic diagram of this apparatus that they used it, right? So first of all, I want to show you the pic. Yes. Now you can see here, as I told you, that the cobalt-60, right? Cobalt-60 nuclei has a non-zero spin angular momentum. Its spin is a 5. It means its spin can be polarized. It can be oriented in a particular direction by applying a magnetic field. You can see here. Now, when the magnetic field is applied in this way, right, and electron spin is in this way, we can say this is the direction of a spin of the this cobalt-60, right? And this is the direction of a magnetic field. And electron are emitted in this direction, suppose, right? Now, when we took the parity transformation, right? In parity transformation, what we should get? We should get this type of observation. If parity is observed, then magnetic field right will be in this direction, right? Spin will also be in this direction because they are axial vectors, they won't be flipped. Whereas the electron emission, it should be observed in this direction, flipped, right? But what we observed in actual, that was this peak, right? When we took the parity transformation, the electron emission, still it is, we are observing the electron emission in this direction. So this is the problem. This is the violation of left-right symmetry here. Otherwise, we should get this image, right, on the parity transformation, on the inversion of the coordinate system, because these are the axial vectors, both magnetic field and spin angular momentum. So they don't change their sign under parity operation. They will remain in the same direction. But once again, I'm repeating, the electron emission that was initially in this direction, Now we should observe the electron emission in this direction, right? If the parity is conserved. But what we actually observed, what Wu and her co-workers found, they found that the electrons were still emitting in the same direction. It means this particular direction is favored in both the right-handed system and in a left-handed system. So this is the violation of the symmetry of the nature. Nature never favor right-handed systems over the left-handed system. This is the simple meaning of the parity. So you can see here the emission of the electron always preferred in one direction in both the systems, right? So this is the violation. So this is what we are going to observe here. We are going to study the direction of the emission of electron in both the ways. One, when the magnetic field is in this direction, and other case when the magnetic field will be in this direction. So in both the cases we are going to measure the emitted electrons directions, right? So this is the whole arrangement you can see here. Now I'm starting with the specimen. So cerium magnesium nitrate along with cobalt-60 specimen, it is placed here. Cerium magnesium nitrate is basically a paramagnetic crystal. So you know very well, if we want to observe this entire process, we have to take a very low temperature, because only in low temperature the cobalt-60 nuclei will remain polarized in a particular direction. Their spin will remain oriented in a particular direction. Otherwise, due to the thermal disturbance, these spins of the cobalt-60 nuclei will be get disturbed, right? So we are producing very low temperature with the help of adiabatic demagnetization of cerium magnesium nitrate paramagnetic crystal. So cerium magnesium nitrate plus cobalt-60 specimen is placed here. You can see here, right? This is here you can see scintillator. It is obviously a anthracene crystal, scintillation counter, right? This is the light pipe through which the light flashes will pass, and here photo multiplied. You know very well the working of a scintillation counter. How does it work? It initially collect the incoming particle, then it produces a tiny light flash, then that light flash is transferred to the photomultiplier tube, and then final counting take place, right? This is the magnet for cooling by, this is the magnet for magnetizing cerium magnesium nitrate and cobalt specimen, right? This is the scintillation counter for the measurement of gamma rays, which are emitted following the decay of cobalt-60 to nickel 60, right? Plus electron plus neutrino, antineutrino. I told you that this nickel 60 nuclei is in the excited state. So when it come down to the ground state, it emit a gamma ray, right? So this gamma rays that are the gamma rays that are emitted following this decay, they are observed by these two counters, right? This one and this one. Now why we are using these two counters? Actually, the gamma ray anisotropy or isotropy is used to check whether the cobalt-60 nuclei is polarized or it is non-polarized. I mean, its spin is oriented in a particular direction, or there is a random orientation of spins. So we can measure that orientation simply by measuring the gamma ray anisotropy, right? I will come to it in the later part. This is liquid nitrogen, liquid helium for cooling process, right? You can see here all these things. This is solenoid coils placed here, for again these are used for magnetization. This is the direction of the initial direction of the magnetic field, z axis, you can see here, right? Now how this whole process will work? I told you that initially what will happen, we will switch on the magnetic field, strong magnetic field. The cerium magnesium nitrate will be polarized, right? Because it is a paramagnetic material, right? And this cobalt-60 specimen will obviously be polarized. It will, its spin will now point in a particular direction, either parallel to the magnetic field or anti-parallel to the magnetic field. It will get a particular orientation. So then after, when both cerium magnesium nitrate and cobalt-60 specimen, they are polarized, then after the magnetic field is switched on. Now when the magnetic field is switched off, what will happen? The cerium magnesium nitrate will try to lose its magnetization, right? And it will produce a very, very low temperature here in this region due to demagnetization. And that low temperature will help in maintaining the orientation of a cobalt-60 specimen, right? But as the time will pass, due to the thermal agitation, thermal energy, right, the cerium magnesium nitrate will lose its magnetization, and then after cobalt-60 will also lose its magnetization, and there will be a total randomness in both these materials. And then after, whatever gamma ray distribution we were getting from this horizontal counter and this vertical counter, these two initially when both these specimen were polarized, we were getting a different counts in these two counters, gamma ray counters, right? And this was giving us the reason to believe that the cobalt-60 specimen is polarized. But as I told you, as the time will go on, this polarization will be lost because the paramagnetic material will lose its magnetization due to thermal agitation, thermal disturbance. We have gone through it in the adiabatic demagnetization process. And then after, the asymmetry between the gamma rays between this counter and this counter, it will get loosed. I'm showing you the graph here. This is the graph you can see here. This is the gamma ray anisotropy graph. You can see here. I'm drawing you this one, right? You can see here the horizontal gamma anisotropy calculated from a counter A and counter B. This is counter A, this one is counter A, and this is counter B. Sodium iodide thallium activated scintillation counter, right? So you can see here, this is the counting rate. Initially, we were getting different counting rate here and here. The two counting rates are different. But as the time here, this is the gamma anisotropy calculated from A and B, and this is the counting rate. So this is actually the time scale, time in minutes. In this direction, we are measuring, taking the time, right? And in the vertical direction, we are taking the counting rate. So you can see here, as the time passes, the two counting rates become equal here, right? It means now the material becomes enough hot that the orientation of the spins got disturbed, right? So then after, we can't say whether parity is violated or conserved, because to observe the parity, whether it is violated or conserved, the spin of the cobalt-60 must be orienting in the particular direction. So that is explained from this graph. So this graph is very important, gamma ray anisotropy. You can see here, right? So when we get the gamma ray anisotropy graph and we observed it, we found that as the specimen is enough cold, right, we are getting different counts of the gamma ray in these two directions. Why we are getting different counts? Because the electrons are emitting in a particular direction, right? That's why, because if you look at the reaction, right, if you look at the reaction, this one, right, as I told you that cobalt-60, this one, right, let me write it here, cobalt-60, that will give you nickel-60 plus electron plus anti-neutrino. So I'm telling you this nickel-60 is further converting into nickel-60 plus gamma ray. So I'm telling you, if the gamma rays are emitting in a particular direction in more number than other, it means the electrons are obviously also doing the same thing. Why? Because the spin of both the sides has to be conserved. We have explained it in the earlier lecture when I told you tau theta puzzle, right? So gamma ray anisotropy is basically pointing toward the anisotropy of the beta rays, right? It means beta rays are definitely getting emitted in a preferred direction, right? So I'm showing you that graph again. You can see here. Now you can see here. Let me check it. Yes. This graph. This is the beta ray anisotropy. Now all these graphs are plotted, on the same page, you can see this is the beta asymmetry graph. Beta asymmetry means it is measuring the number of electron emitted in the direction of the magnetic field and in the direction opposite to the direction of a magnetic field, right? So you can see here we are getting different number. Let me show you this graph here. This graph is also plotted. Yes, you can see. So when we observe the counting rate, right, from this counter, that is this counter, scintillation counter, the number of beta particles emitted when the spin is pointing in one direction, when spin is pointing in another direction. So it is found that more beta particles are emitted in the direction in which in the direction opposite to the direction of applied magnetic field. You can see here, right? This is the direction of applied magnetic field and this is the opposite direction. So it is observed that more electron magnetic field is pointing in this arrow means magnetic field is pointing in this direction, magnetic field is pointing in this direction, right? Now when the magnetic field is pointing upward, the more electron are obviously the electron will emit in the downward direction, right? And when the magnetic field is pointing downward, then in that case the electrons will be emitting in the upward direction, obviously, right? This is the case because of the law of conservation of angular momentum. But as we change the magnetic field and we measured these two rates, it is found that more electrons are emitted in this case as compared to this case. It means more electrons are emitted in the direction opposite to the direction of applied magnetic field. This is H and this is the direction of emission of electron. So this is the clear-cut indication that I was saying here that the electrons emission is preferring a particular direction, right? And it is and you can see here in this graph also that after some time these two graphs will become equal or they will coincide. Why? Because now the polarization of the cobalt-60 nuclei will get lost because of the heating of the specimen and because of the loss of paramagnetism of cerium magnesium nitrate, right? So this is the role of this time scale. The same time scale was there in case of a beta ray anisotropy, right? You can see here these two graphs, right? So this is the experiment that confirms that the parity conservation is violated, and this experiment was, as I told you, it was performed by Wu and her co-workers in 1956, right? So once again, you can see this graph counting rate in the case of particles, emitted in the direction of magnetic field and in the direction opposite to the magnetic field, right? So this is all about this violation of parity conservation in beta decay, right? So thank you very much.